Alright guys, for the final lesson of Chapter 9, we are going to take a look at something called math induction. You may or may not have seen this within Honors Algebra 2. It's often given a day's lesson in Honors Algebra 2, but I know it just kind of depends on what your teacher decided all to show you last year. So let me go through this with you. It's a few steps of a process. It's basically a way of proving that the rule for a sequence is true. And so what we're going to take a look at are kind of three basic steps here of how this process works. The first one they call the anchor. So what you're seeing on this one is on the left side of the equation you are seeing a sequence. So 1, 2, 3, 4, 5, on and on and on. And it ends at whatever term n is. On the right side you are seeing the rule for that sequence. And our goal is to basically go through these three steps and to prove that this rule is true for this sequence over here. So the first step is, let's just prove that it works for the first term. So if this is my rule, that means when I plug in a 1 for n, the result should be the first term of the sequence. And so that's just the first step, is they say, okay, let's just plug in a 1. So 1 squared plus 1 is 2, divided by 2 is 1. So sure enough, yes, it works for the first term. So that's like the first step in the process. The second and third steps really go together, but it's basically saying, okay, we've proven that it works for the first term in the sequence, so it works for terms n. So now our goal is to prove that it works for all successive terms after that. So the second step, which has always been a little bit weird to me, I don't even know if I could tell you a good reason as to why they have to take the second step. But they basically take this same layout and they replace all of the n's with k's. So it looks like this. Don't know really why that's a necessary step, but that's the second step that you're going to take. That's the second step in the process. The third one is this, and to me this is like the key step here, is we are going to take this equation that you see right here, right? And essentially we are going to add k plus 1 to both sides of the equation, right? If k represents any term, k plus 1 would obviously represent the next term. So as we've already shown in the first step that it works for this singular term, it works for a term of n, we're now going to show that it would also work for the next term in the sequence, which would be k plus 1. So we are adding k plus 1 to both sides of the equation. So that's what you are seeing right there and right there. Right? So everything else has remained the same as what we started with right here. So in this third step, you're adding k plus 1 to both sides of the equation. That's always what you do in the third step. And here's kind of what we're looking for. If I simplify this, if it works, what we should see is I get the exact same formula that I started with. However, k is now k plus 1. So let me show you what we mean by that. So the first thing they did on this is they said, okay, well, we're adding two fractions together. Let's create common denominators. So they multiplied this guy by 2 over 2 so that they could combine these into one big fraction. They do a little distribution, combine like terms, and they go through a little bit of a process on rearranging terms in order to see this perfect square. They factor it and it comes out looking like this. So here's what we're seeing here. You'll notice that this is the exact same formula that we started with. Looks exactly like this, except now instead of k, we're seeing k plus 1. So this is now going to read as k plus 1 squared plus k plus 1 over 2. And so that's kind of the final goal, is as we added k plus 1 to both sides of the equation, we're now seeing that the new rule has now become k plus 1. Right? And so that's like the third and final step of math induction. Right? And so they got some sort of special names for this. It's not really that big of a deal if we know the vocab for that, but more of just understanding the process and kind of how this proof works for sequences. So let's try it on this one. We have this this nice arithmetic sequence taking place right now. So first things first is understand where this 3n minus 2 came from. If you go back to our formulas, all right, this is one we've been working with for the last couple lessons. All right, this is simply an arithmetic sequence where they are adding 3 every time to get the next term in the sequence. Well, if we were asked to write the general rule for this sequence, we would plug in a 1 for the first term, we'd plug in a 3 for D, and we would simplify it, and if you did that, you would get 3n minus 2. So this is the general rule for that sequence. And so what they're saying is prove, so now we're using the math induction process to prove that this rule on the right is true for all terms within that sequence. Right? So it's like we're kind of proving a different rule here to be true for this pattern of numbers. So first things first, step 1 is to plug in a 1 for n and show that it does give us the first term in the sequence. So if I put in a 1 for n here, right, I would be looking at a 1, and I'm just going to write this out so we have it for notes. So 3 times 1 minus 1. All over 2. So this is our first step. Okay, so I'm plugging in a 1 for n, and sure enough, 3 minus 1 is 2, divided by 2 is 1. So sure enough, step 1, good to go. Plugged in a 1 for n, and it did in fact give us the first term of the sequence. So now we have to show that this works for all successive terms. So in step 2, this is where they will now replace all of your n's with k's, right? And so this becomes 3k minus 2 on the left. And on the right, we're just going to, again, just replacing the n's with k's, so it becomes k times 3k minus 1 all over 2. Okay, so that's our second step. So here's the third step, and this is the key step, and I want to make sure I clarify something that we did on the first example, because what I wrote here of adding k plus 1 to both sides, I had something here previous, and I had sort of deleted it and rewrote this for this specific problem. But let me make sure this is clear. Why did we add k plus 1 to both sides? Well, if my rule on this side was k, obviously, again, k plus 1 represents the next term. So we replaced this k with k plus 1, and that's what we added to both sides. So here's why I'm telling you that. So I got to do the same thing on this one. If I replace this k with k plus 1, well, what would that look like? So let me keep what I already have. So if I replace that k with k plus 1, it's going to look like this. Right? So it's not just adding k plus 1 every single time. It's using the rule that's on the left, replacing k with k plus 1, and whatever that becomes is now what is getting added to both sides. So this is being added to both sides. So we took the rule that you saw here. I replaced k with k plus 1 so that it would represent the next term in the sequence. And if this is now the next term in the sequence, so if that's what's being added to the left side, so I guess I put a plus sign right there. So if that's what's being added to the left side, well, then I got to do the same thing to the right side to match it. So again, I'm keeping what was already here. but I am now adding to the right side the same thing that I added to the left side. And let me turn that into a plus. That's what it's supposed to be. Because this is a series, and obviously this is being now added to both sides of this equation here. So I'm also going to add this to the right side, and you could simplify it first if you want to. If I distribute, it's going to be 3k plus 3 minus 2 is going to become 3k plus 1. But just in case, I guess I'll write it all out for the sake of notes. Okay, so this now got added to both sides of the equation. Again, because this was the previous term, we replaced this k with k plus 1, and that's what got added to both sides of the equation. Okay, so now the goal is, I should, if this proof is correct, I should be able to simplify all of this. And what we are looking for is, it should look like the original rule with the k's replaced by k plus 1s. So, in other words, it's going to be the exact same rule that I see here, but instead of this being k, that should be k plus 1. And instead of this being k, that should be k plus 1. So that's the goal. So let's do a little cleanup here. A little distribution. I'm going to try to see if I can take a little shortcut here, but I'll just write it out. So on this one, again, if I simplify this chunk, it's going to become 3k plus 1. And I'm going to multiply it by 2 over 2 so that I can combine these two fractions together. So this is now going to become 6k plus 2. Alright, so here's what we got right here. Let me take one more step. Combine like terms, so 3k squared plus 5k plus 2. And I'm going to run out of room here, so I'm going to have to continue on this side. Sorry if you hear my kids yelling in the background. They got some kind of intense game of Brawl Stars or something going on downstairs. So, alright, so 3k squared plus 5k plus 2. All over 2. I don't mean for it to look this chaotic, but I ran out of room, so we're going to continue over here. Okay, if I factor this, let's see, factors would be 3k plus 2, k plus 1. So keep in mind what I'm looking for right now, because you might look at this and say, well, that's really as far as you can go. You really can't go any farther than that. And that's kind of true, but remember the goal is I'm trying to get back to this idea. I need these to look the same, where this is a k plus 1 and this is a k plus 1. And it doesn't really look like that yet. So I do have this, right? Instead of that n right there, that's a k plus 1. So my goal is how can I make this look like this, where that variable is k plus 1. And this is where it gets a little tricky, and you got to play with it a little bit, but the idea is we could do something like this. For this, I want this to be a 3 so that I can factor out 3 as a common factor. So what we're going to do is I can add 1 to this as long as I also subtract 1. So what they would say is, let's add 1 and subtract 1, right? Because if I add 1 and subtract 1, then technically I haven't changed the value of what I have, right? Because that still would cancel each other out, and it gets me right back to what I started with. So I haven't changed the value of anything, but that now allows me to write this as 3k plus 3 minus 1. So my video cut out a little bit here, so I'm trying to, it paused and then I kept going, and so let me explain how we finished this one off. So again, as we wrote this 2, what we did was we put the +1 and the -1 so that this could be written as 3. Again, sorry about the noise behind me. I got a dog going nuts at my kids downstairs. So anyway, so we have this look right here, and the whole point of doing that was so that I could factor out 3 as a common factor. And if I did that, this would be the new look. But you'll notice here's obviously why I did that is this now exactly matches the rule that we started with. However, that n has been replaced with k plus 1, and that n has been replaced with k plus 1 as well. So the proof worked. That was it. That's how the process goes. I did one thing up above while I was trying to figure out my video stuff. And so I rewrote, because what I had here originally was mainly for this specific problem, but I thought maybe I should rewrite it to fit all problems rather than just this one specific one. So if you want, you can alter your notes a little bit to maybe a little more accurately, broadly approach all problems rather than this one specifically. And so that's what I put in there. So let me go on to this next one here. And again, let me just sort of talk you through the process. So I have one at the bottom that I want us to do together. And so let me, again, kind of show you what they're doing. So step number 1, first thing they're going to do is, in looking at the layout, right, 1, 8, 27, you probably see the pattern already, is any term number to the 3rd power. Okay, so what they're wanting us to prove is that this is also equal to this rule on the right side. And so here comes the induction process, and the first step is to replace my n's right here with a 1. And in doing that, it should equal the first term of the sequence. And sure enough, it worked for this one. Step 2 is then to replace our n's with k's. Okay, and so here's the new look if you replaced your n's with k's. And so here's the key 3rd step, right? And this is kind of the super important piece of this that we have to get right before going through all this algebra that you see that follows. So if my rule over here is k to the 3rd, I need to replace this k with k plus 1 in order to represent the next term in the sequence. So instead of k to the 3rd, it now becomes k plus 1 to the 3rd. And of course, if I add that to the left side, then I also have to add that to the right side. And then ideally, when I simplify it, my final result should look exactly like this, but instead of n, I should see a k plus 1 here and here. Right, and so that's what they ended up getting. If you were to follow the algebra, it's pretty basic, even though it's a little tedious. And that's the way that process works. So let's go through another one together. I just thought it'd be worth the practice, so follow along if you want to do another one of these with me. And who wouldn't, right? So here's the general layout. You can see it's arithmetic. They're adding 6 every time, which is where they came up with this rule. And so what they want us to prove is that this rule also works for all successive cases on the left side. Okay, and so step number 1 is going to be to replace our n right here with a 1. And in theory, it should give us the first term of the sequence. So 3 times 1 squared is 3. So step number 1 is good. So step 2, replace our n's with k's. So this becomes 6k minus 3. Over here, we're looking at 3k squared. Kind of nice when it's a little simpler here. All right, that's step 2. Step 3, and here comes sort of really the important induction process here is I'm looking at this rule, and if I were to replace that k with k plus 1, so the next term in the sequence would be 6 times k plus 1 minus 3. And yes, you could simplify that. I'm just leaving it like this for the sake of notes so you guys remember where all this stuff came from. But if that's what I'm adding to the left side to represent the next term, then I should also be able to add that to the right side. And when I clean this up, it should look like this exact same statement here. However, my n should get replaced with k plus 1. And so this is the look that we're hoping to come up with. Okay, and so as we do a little cleanup on this, so obviously 6 minus 3 is 3. We're also going to be able to factor out 3 as a common factor, but I won't skip steps on you. So let's take out that 3 as a common factor, and that's what we expected to see. And of course that is a perfect square that could be written as k plus 1 squared. And voila, right? We're getting that exact look that we were hoping to come up with, and that's the end of our induction process. Let me take you to one last thing on the back here, and then we will call it quits. So this last one that I wanted to show you is really the same thing. It's just it's a little bit of a different description and layout, so but really the same process that we're going to be going through. But what they're saying on this one is they want us to prove that 5 to the n minus 1 is evenly divisible by 2 for all positive integers n. So I'm going to go quickly through this, and then we'll just do one together, and that'll be it. So they're going to take the same 3 steps. Okay, and so first thing they're going to do is they're going to say, well, let's plug in a 1 for n and see if it's true. So if I did 5 to the first minus 1, I get 4, which is obviously divisible by 2. So first step is accomplished. It does work when n is 1. Okay, and the rule holds true. Step 2, we are still replacing n with k. So 5 to the n minus 1 became 5 to the k minus 1. And so again, we're just basically saying, okay, we assume this is true. Still true that it's still divisible by 2. Let's go to the third really main inductive step here that we're going to go through. So we are now replacing k with k plus 1. Okay, and so that's the exponent that you're seeing right there. Sorry if it's not that clear. But we need to now say, okay, well, if that represents the next term in the sequence, we need to show that this is also divisible by 2. Okay, and so here's where it gets a little bit tricky. So see if you can track with me on this. But they're saying, okay, here's our new statement. They basically want to rework it to show that the terms of their solution are all divisible by 2. So here's what I mean by that. We know that 5 to the k plus 1 is the same thing as 5 times 5 to the k power, right? Think of this as 5 to the first, and this is obviously 5 to the k. Well, when you multiply common bases, remember the rule is we add their exponents together. So when you have, I'll just write it. So when I have 5 times 5 to the k, right? Well, again, I'm allowed to combine those common bases by adding the exponents together to get that statement right there. So that's essentially what they did, almost like working backwards. We were starting with this, and they broke it up into those 2 terms. And so that's where they got this statement right here. So 5 times 5 to the k, they just kept this. The minus 1 was just like brought down. So from there, they wanted to show that 5 to the k minus 1 can be written as a factor within this problem. So they wrote it this way, right? So instead of just saying 5 times 5 to the k minus 1, they threw this 5 to the k minus 1 in parentheses, right? But obviously, if you do that, well, if I distribute the 5, I not only get 5 to the k plus 1 here, but then I would have minus 5 instead of minus 1 if I distribute, right? Well, that would change the value, obviously, of what we have. Having minus 5 is not the same as having minus 1. So they said, okay, well, if this is now minus 5, let's add 4 to the end of this, to balance it out. So now technically overall, I do have what I had right here, right? Because they subtracted 5, but they also added 4, which is a total of -1. I know it's like was a little unclear, but I kind of reasoned through how they did this. But so here's what they're showing is if I look at these two terms, this is my first term, this is my second term, it still fits the description because each term is divisible by 2. 4 is obviously divisible by 2. They're also saying this is divisible by 2 because this factor, 5 to the k minus 1, we already showed back here was divisible by 2 when we plugged in the 1 for n. Okay, and so they're saying, okay, so if each of these factors are divisible by 2, then the whole thing is divisible by 2. There's our induction. So little weirder of a process on this one. Let me go through one with you guys. There we go. So guys, even though I originally circled 15, we're actually going to look at 13. It's a little more similar to the one that we just did, plus it's a little more similar to the ones that are actually in the textbook. So I thought this would be a better one for practice for you guys. So if we're going to prove that 18 to the n minus 1 is evenly divisible by 17, again, we start out with that same first step where we plug in a 1 for n. So 18 to the first minus 1 is obviously 17, and yep, that is divisible by 17. So we're good to go on that one. Step 2, this is where we replace our n with k. So we're now looking at 18 to the k minus 1. So in step 3, so this is where we replace our k with k plus 1. So we're going to say 18 to the k plus 1 minus 1. So again, our goal now is to prove that this is divisible by 17. So we're going to try a similar attack to what they did up above. And so remember, I can, for the same reason they split this up above, I can do that here as well. So I can see that as 18 times 18 to the k power, right? Because if I add those exponents, bring it back together to get 18 to the k plus 1. So I am allowed to separate those. We would like to put parentheses around this entire factor so that we can see this separated from that 18 right there. So what we're going to do is we're going to pull out that 18. We're going to write 18 to the power of k minus 1. So it looks like this. So essentially all I did was throw in parentheses, but that definitely changes the value of what I have now, right? Because this was just minus 1. Now it's technically minus 18. Because that 18 distributes and now belongs to him because of the parentheses. So I wanted it to be -1. Now it's -18, so I have to add 17 to this in order to balance it out. So now if I were to simplify this statement, now it would bring me back to what I had in the previous statement. But now as I look at that, for the same reason above, we've actually made our proof, because I now can see that 17 can divide evenly into all terms, right? If I look at my second term, obviously 17 goes into 17. If I look at my first term, as long as 17 divides into a factor of this, then we know we're good to go. So we've already shown that 18 to the k minus 1 is a factor that is divisible by 17. And so now I can see that 17 goes into this term, 17 goes into this term, so we're good to go by showing that the whole thing is divisible by 17. So that is it for, well, that's it for all of chapter 9.